Sorry, dear students, there was a tremendous network issue. Since morning, I'm facing this problem. Okay, so we'll start today's class. It's already time. Hope others will join. No problem. We will discuss about, yesterday we discussed about block architecture. So today we'll discuss about HCFC, HDFS data node and name node. Okay, that's part of HDFS architecture. So name node, we have already seen. Name node is the one which holds the what we call it as what we call the metadata, number of files, what is the number of replication, is the IDs. So yesterday we discussed this. So a file name called part0 is having two replication, and it is split into two blocks. The block ID is 1 and block ID is 3. So 1 and 3, you observe here, 1 and 3 will never be stored in same computer. Observe there, the file 1 and 3, they are stored in different computers, 1 and 3, and they maintain a replication of 2. Sorry, again it got disconnected. No, network issue probably. Okay, so I have been yeah, yes, look at here. So part 1, actually it is having replication 3. That means it is divided into 3 blocks. Block number 2, 4 and 5. 2, 4, 5 never stored on same machine. You can see 2 is stored, 5 is stored, 4 is stored. 1 copy, second copy, 2, 2, 2, 2, 3, 3 times replication factor is 3, it stores. And it will never store on the same rack. The second cap, this is one rack, this is second rack, this is third rack, this is fourth rack. So your name node is so intelligent, it will never store on the same rack. That's very, very important thing that you should understand. And it will never store on the same rack. So rack number 1, rack number 2, rack awareness. That is called rack awareness. So based on this, in order to check the disk blocks in the HDFS file system check is the command which will start from root of the file and stores, displays all the files and how many blocks they have taken, what is the replication factor. So I have already installed Hadoop on my machine. I'll show you, I'll take you to, this is a Hadoop machine. I have, I have written, I have installed everything in Hadoop machine. So right now, I don't have, missions. So if the same mission, if I can, connect in my college lab LAN, so I will be able to use multiple data nodes, multiple, name nodes, I can certainly use. Now, so in this Cloudera, actually I have used Cloudera. Cloudera is one of the flavor of your big data Hadoop. Hope I am audible, right? Most of you? Hello?
Yes, sir. Yes, sir.
Yeah, thank you, Sai. That's what I was just talking about. So if I give the same command, Hadoop file system check from the root node and all the files and total number of blocks, what happens? It will display a report containing all the files, how many blocks each one has taken. See, this has given. So many blocks are there, so many blocks replicated, so many, finally. So missing replication, and finally it says the data node is healthy. This healthy report only, it is very much required that I need to send it to data node, my name node every time. So if I issue this command Hadoop, the command, so it will say, so what is the length of the file, how many blocks are there, see what is the block 1, what is block 2, everything. This is what we call it as block report. This block report along with the health of the each data node will be sent. It will be sent to the uh, name node every 1 second, every 3 seconds. So the command, I think I have already given Hadoop fsck root and files and blocks. So this is the command that we have to give. So this is what we discussed. Now we'll discuss in detail about what is name node and data node. So actually, name node and data node is actually a master slave architecture. So that means Hadoop name node is actually the master, and Hadoop data nodes are workers. Workers in the sense, so they store data, and always whatever the name node gives the instruction, the master instructions will be followed by your data nodes. Fine. And name node manages the file system namespace. It maintains the files system tree and metadata for all the files and directories that it has. And not only that, this information is stored persistently on the local disk of the, so that is, it will store namespace image, and also it will hold edit log. So edit log, who does what job, everything, it is being recorded here. And name node also knows the data node on which the blocks for the given files are located. However, it does not store any block location persistently, since this information is reconstructed from data node when the system restarts. Of course, that is one of the very important thing. So client accesses the file system on behalf of the user and communicates to the name node. And remember, if you have a name node, I've written name node, this is name node, and all your data nodes are connected to name node. Okay, all your data nodes are connected to name node like this. And of course, you can see all data nodes are connected. So all data nodes are connected, all data nodes are connected, all data nodes are connected like this. So the client normally will talk to, the client will always talk to the name node. He will talk to name node. So he will talk to name node, and he will send a file to name node, and whatever the file that name node receives, it will split and it will send it to all the data nodes, all the data nodes. So this is how the actual functioning happens. And if you look at all these operations, whatever operations that is happening, everything is taken care by, entire operation is monitored and taken care by your name node. And data node only stores data and follows the instructions from the name node. And the client presents a POSIX-like file system interface. So that is a Unix system interface. So the user code does not need to know about the name node and data node functions. So this is very, very important. And not only that, you observe here. So whenever name node gets the data, name node maintains the metadata. That is name, number of replicas, how many blocks, everything. Client will send data to name node, and whenever client want to read the file, again client will send a message that instruction I want to read a node. It will tell what are all the blocks in which the data are stored to the client. So client will certainly, read all the data from data nodes. He will read the data. So such many clients are connected to name node. See, client 1, client 2, client 3, client 4, many clients. Each client will be referring to various racks in the data nodes. So each data node is consisting of many racks, and of course, it is. Sometimes these replications are not within the same data node. It will be different rack, and it will be different data node with the different location, and that's how the failure can be easily handled, and that's one of the very important node. So data nodes are workhorses for the file system. They store and retrieve blocks when they are told by the clients or to the name node. So if name node tells, and observe one thing, they always report the heartbeat instructions to the name node periodically with a list of blocks and their health, etc. So if the if the report is not being sent to the data node automatically, data node, if they fail to send report, the name node will understand that oh, data node has gone down. Without the name node, the entire file system could not be used. So name node is the main person who has all the data, what do you call, metadata information, which node, which file, where it is stored, which data node, everything. Suppose you have a question. Suppose if there is a problem with respect to, what do you call, if there is a problem with respect to data node, name node itself, if something happens to name node, so there are chances that name node is also designed on a commodity hardware. There may be chances that name node also can be crashed. So if a name node crashes, the entire system goes wrong. So that is why we have another concept called secondary data node. Secondary data node also works simultaneously with the name node. Suppose the main primary name node goes out, the secondary node name node will immediately come into picture. In fact, if the machine running the name node were obliterated, all the files on the system would be lost, since there would be no way of knowing how to reconstruct the file system from the blocks to data nodes. For this reason, it is important to make a name node resilient to failure. Very, very important. Hadoop provides two mechanisms for this. Very, very important. See, Hadoop knows very well data node is name node is very, very important, and Hadoop provides the failure resilient to name node. Name node should not fail at all. It should not fail at all. So Hadoop provides two mechanisms for this. So one is the first one. The first way is to take backup the files that make up the persistent state of file system of metadata. Hadoop can configure so that name node writes the persistent state to multiple file location. Definitely. So the name node itself, it is maintained a backup. So if suppose main name node goes down, another name node, secondary name node, will come into existence. So second one, these writes synchronous and atomic usually configures the choice to write the local disk and remote NFS mount. NFS, so we call it as new file system. So it is another file system that certainly mount. So it maintains a backup copy. Suppose the entire node doesn't fail, secondary name node doesn't fail, but what happens? only a particular disk is failed. So in that case, what happens? Name node can recover it with that backup disk. If the entire name node goes down, it is also possible to run a secondary name node. So which, despite its name node, does not act like a name node. Its main role is to periodically manage the namespace of image, and it will check the health of the name node. If the name node health is gone, automatically secondary name node will become the name node. So that is one very important thing that you should observe. The secondary name node usually runs a separate physical machine, since it requires plenty of CPU and as much of memory as a name node to perform and merge. So what happens? It keeps the copy of merged namespace images, which can be used in the event of main name node failure. If the main name node fails, automatically what happens? The secondary name node will come into play. Very, very important. However, the state of secondary name node lags that of the primary, so that in the event of failure of primary, the data loss is almost certain, and in that case, it will. The usual course of action in this case is to copy the name nodes metadata files on the NFS new file system to the secondary name node and run it as a new primary node. So primary name node. So that's how it is done. You can see here, HDFS client will always talk to name node and observe one very important thing. One very important thing is that this particular name node will always be backed by the secondary name node. And you observe here all its metadata is stored in FS image, file system image. So it is. And every time the information replication, the balancing factor, heartbeat information, etc., every time the data nodes used to send back to the name node. Data nodes has to be sent back. So they have to send back, they have to send back to the name node. If something sometimes goes down, it automatically creates one more name node. It will create one more name node with the same data. So it has backup. So all these with the FS image, it will create another data node. Suppose if this itself goes down, so automatically the secondary name node from the FS image, it will become the primary node. It will go into the position of primary node, and it will take up this. So this is very complicated process, but Hadoop handles it very fantastic way. In a fantastic way it handles. So let us see what is that supercomputer center at Santiago. People they talk about this. So yesterday also we stopped at beginning. We'll see what is exactly what they talk.
The Hadoop distributed file system is a storage system for big data. Is the storage layer. The Hadoop distributed file system, or the way we call it HDFS, serves as the foundation for most tools in the Hadoop ecosystem. It provides two capabilities that are essential for managing big data: scalability to large data sets and reliability to cope with hardware failures. HDFS allows you to store and access large datasets. According to Hortonworks, a leading vendor of Hadoop services, HDFS has shown production scalability up to 200 petabytes and a single cluster of 4,500 servers with close to 1 billion files and blocks. If you run out of space, you can simply add more nodes to increase the space. HDFS achieves scalability by partitioning or splitting large files across multiple computers. This allows parallel access to very large files since the computations run in parallel on each node where the data is stored. Typical file size is gigabytes to terabytes. The default chunk size, the size of each piece of a file, is 64 megabytes, but you can configure this to any size. By spreading the file across many nodes, the chances are increased that a node storing one of the blocks will fail. What happens next? Do we lose the information stored in block C? HDFS is designed for fault tolerance in such cases. HDFS replicates, or makes a copy of, file blocks on different nodes to prevent data loss. In this example, the node that crashed stored block C. But block C was replicated on 2 other nodes in the cluster. By default, HDFS maintains 3 copies of every block. This is the default replication factor, but you can change it globally for every file or on a per file basis. HDFS is also designed to handle a variety of data types aligned with big data variety. To read a file in HDFS, you must specify the input file format. Similarly, to write a file, you must provide the output file format. HDFS provides a set of formats for common data types, but this is extensible, and you can provide custom formats for your data types. For example, text files can be read line by.
Sorry, students, the line got disconnected. So I had to rerun the, video. Okay, anyhow. So this video is very informative. That's the reason. Hope I am audible, right? Hello? Hope, am I audible?
Yes, sir.
Yeah, thank you. Thank you.
Yes, sir.
Like FASTA or FASTQ formats for sequence data in genomics. HDFS is comprised of 2 components, name node and data node. These operate using a master-slave relationship where the name node issues comments to data nodes across the cluster. The name node is responsible for metadata, and data nodes provide block storage. There is usually 1 name node per cluster. A data node, however, runs on each node in the cluster. In some sense, the name node is the administrator or the coordinator of the HDFS cluster. When a file is created, the name node records the name, location in the directory hierarchy, and other metadata. The name node also decides which data nodes to store the contents of the file and remembers this mapping. A data node runs on each node in the cluster and is responsible for storing the file blocks. The data node listens to commands from the name node for block creation, deletion, and replication. Replication provides 2 key capabilities, fault tolerance and data locality. As discussed earlier, when a machine in the cluster has a hardware failure, there are 2 other copies of each block that was stored on that node, so no data is lost. Replication also means that the same block will be stored on different nodes in the system, which are in different geographical locations. A location may mean a specific rack or a data center in a different town. The location is important since we want to move computation to data and not the other way around. We'll talk about what moving computation to data means later in this module. As I mentioned earlier, the default replication factor is 3, but you can change this. A higher replication factor means more protection against hardware failures and better chances for data locality. But it also means increased storage space is used. As a summary, HDFS provides scalable big data storage by partitioning files over multiple nodes. This helps to scale big data analytics to large data volumes. Replication protects against hardware failures and provides data locality when we move analytical computations to data.
So that's the video that talked about how exactly people of supercomputers Santiago opinioned. So name node, data node, and for every node, either it may be a data node or name node, there will be a backup system. So this backup system works very well. Backup system works very well, and of course that's why Hadoop system is called most fault tolerant system. So it is one of the system in the efficient system that are being used for handling big data analytics. And in the next class we'll be discussing about Hadoop Federation. Meanwhile, I'll also do a short revision on this module 1, so that it becomes very easy for you to take up the test. Meanwhile, I have been instructed already. Everybody, you sign up to Google Class. So I have shown how to sign up to Google Class. Hope everybody, you should know. I think you should have done it. So everybody, please sign up to join Google Class. The Google Class code also have already shared in the WhatsApp. So kindly do it. That's all. Today's class recording will be available in this website, and we will discuss some more concepts in the next upcoming class. Have a wonderful weekend. Thank you.